Okay, hi everyone. I want to just give you a few reminders about modular arithmetic and some pointers, some things to keep in mind that might be helpful going forward in number theory. So let's just recall the definition. We say, I guess we say in words, A is congruent. I really should say given A and B in the integers. And in fact, given A and B and Z and M not equal to 0, we say A is congruent can I spell? To B mod M modulo M, and write, what do we write? We actually write something like A is congruent to B mod M. It's supposed to just be 3 horizontal lines. If and only if, so the definition is if and only if, basically the definition is that A and B are off from each other by a multiple of M, right? So one way we can say that is if and only if there exists an integer K such that A equals B plus M times K. Okay, just, that's the definition. And as an example, or examples, we could say something like 11 is congruent to -3 mod 7. Because why? Because can we solve the equation 11 equals -3 plus 7 something? 7 times what? Well, 11 is, if you take -3 and you shift it up by 7 twice, right? You get 11. So the one way I think about this is like, say we're on the number line and here's -3, maybe here's 0, here's 10, here's 11. Then I think, okay, well, we start here and we jump by 7 and I guess we end up at 4 and we jump by 7 again and we end up at 11. So I kind of think of starting somewhere, hopping around left and right by 7s and seeing if you can land on the other number. I don't know, for some reason numbers are very geometric to me, the number line. So this is certainly true that 11 is congruent to -3 mod 7. Maybe another example, how about 4 is congruent to 20,004 mod 1000. Because again, 4, we know if we go from 4 to 20,004, we go by 20,000, which is a multiple of 1,000. So 4 is 20,004. Well, plus 1,000 times what? Well, I'm actually subtracting, I guess. So it's really times -20. Right? Okay, I think you guys are comfortable with that. I just want to mention some other definitions or equivalent definitions. Sometimes you see it presented different ways in different books, and sometimes it's just more convenient to write it different ways. So you could say A is congruent to B mod M. Another way to think about this is the difference, right? The difference, if you think about A minus B, it's got to be a multiple of M, right? Like in this case, 11 minus -3 is 14. That's multiple of 7. 4 minus 20,004 is -20,000. That's a multiple of 1,000. So you can say if only if M divides A minus B. That's one equivalence. Another equivalence, and this is sort of helpful as you go further in math, is you can also just say that a minus b lives in the set of multiples of m. So this is the set of multiples of m. So for example, like 7z is the set that includes 0 and 7 and 14 and 21 and so on that way, and minus 7 and minus 14 and so on that way. Right? And so, for example, the example we did above with 11 and -3, the difference is 14, which lives in that set. Okay, so those are some equivalent definitions we'll use at times. It's nice to keep these in mind. An important property is that mod m is an equivalence relation. Maybe a note or a reminder. Mod m is an equivalence relation. You remember those? Equivalence relations are things really that basically act like an equal sign. So it's reflexive, that a is congruent to a mod m. It's symmetric. I'm not going to write these all out, but you might write them out for yourself. If a is congruent to b mod m, then b is congruent to a mod m. And it's transitive. If a is congruent to b mod m and b is congruent to c mod m, then a is congruent to c mod m. Okay. So, and that's a useful thing because we can think about the equivalence classes. So we could think about like the 1 mod 7 equivalence class or something like that. Everything that's, you know, in fact, I'll even just write like equivalence classes. For example, something like, you can even say something like 1 plus 7z, which is a set of all things that are 1 mod 7. So you'd have 1, you'd have 8. Actually, let me do 4. I don't know why I didn't think of this before. Let's do 4 because I think that's the example that we had. You've got 4, you've got 11, you've got 18, you've got 25 going that way. But you got -3 and you got -10 and et cetera going that way. And so, right, we had that example with these two guys. Sorry, my pen stopped working for a second. Example with these two guys being congruent to each other. So two things in the same equivalence class. The other thing that's super important, so moreover, what I'm going to say is that, moreover, as an important thing is that the operations plus and times sort of the way the word mathematicians use is respect the equivalence relation. And this is super important. Well, what do I mean? What I mean is if you take two things in the same equivalence class and add them, or say take two things and take things in different equivalence classes and add them, you get something in another equivalence class. But it didn't matter what you chose. It didn't matter what representative you chose. Let me say this a little better. So there's a proposition here, which is that so just given A, B, C, and D, to quantify all my variables, right? M not equal to 0. I mean, you could talk about mod 0 if you want, but that's not very interesting. Mod 1's not very interesting either. Anyways, neither here nor there. So if we have A congruent to B mod M and C congruent to D mod M, then that means A plus C is congruent to B plus D. And A times C is congruent to B times D. Right, so what I'm saying is it doesn't really matter what representative. Remember, the every element of an equivalence class is called a representative. So we can represent the 4 mod 7 equivalence class by any number like 11, -3, 4. And it doesn't matter. Like, as an example, you know, I mean, we can just check an example. I do want to I want to sketch the proof of this just briefly because it's, or at least proof of one of these because it's nice, but you know, we said 11 is congruent to -3, mod 7. Let's pick something else. 2 is congruent to 9, mod 7. And if we multiply these, like 11 times 2 and -3 times 9, then let's just check. 11 times 2 is 22, which is 1 more than 21. So that's 1 mod 7. And -3 times 9 is -27. Oh, but -27, if you add 7 to it 4 times, right? If you add 28 to it, you get 1. So just putting this to the side, these imply that 11 times 2 is congruent to -3 times 9, mod 7. Okay, so that's nice. Just to sketch, maybe I'll just sketch the proof of the multiplication one. It's a little more interesting. So proof sketch. Let's call this, if I call this 1 and I call this 2, then I want a proof sketch of 2. Maybe I won't do it super, I was just saying sketch because I'm not gonna do it super axiomatically, but just think about it. If A is congruent to B mod M, then you can write A is B plus MK. So that's what I'm saying sketch. I'm not writing A is congruent to B mod M, so there exists a K in Z such that A equals B plus MK. I'm just writing A equals B plus MK. And C equals D plus M. I need to use a different letter, L, right? And then if you take AC, multiply A times C, you get, and then if you FOIL this out, you actually get BD plus, well, you get an M, and you can factor it out. Let's see, I think there's a KD and a BL. You can check my letters, and an MKL. And so there's an M times something, right? This is an integer. This is an integer. And so that means that AC is congruent to BD because they're off for each other by a multiple of M. Okay. And yeah, again, that's really important. Okay, so it's important sort of theoretically because it's actually going to let us define these finite mod rings. Like Z mod M is actually a ring because you can do multiplication and addition in them. I'll talk about that in the next video. But also it's helpful computationally. So let me just give an example here. A couple examples. This is something we're going to use a lot this semester, so you should keep it in mind whenever you're trying to do computations. So example, if you want to compute, say you want to compute something kind of big, right? Like 511 times 707 mod 100, right? You want to multiply this together and reduce mod 100. Well, you don't actually have to multiply all that out and then reduce mod 100. You can just say, you can reduce first, then multiply. Instead of multiply, so instead of, you know, multiply then reduce, it's easier to, and it's okay, it's easier and it's kosher to reduce than multiply. So, 511 times 707 is actually congruent to 11. 511 is congruent to 11, clearly, and 707 is congruent to 7, which is 77 mod 100. So we know that it's something that kind of intuitively, right? The product of 511 times 707 is going to end in 77. Okay, another example. This is something that's going to come up a lot. Say we want to compute something like powers. This is going to come up a lot in cryptography. Say we want to compute 2 to the 8th mod 11. Well, you could, this is not, I'm using a sort of small number just to illustrate this, but 2 to the 8th is not that big, it's 256. And then you could reduce that mod 11. But you can also say, well, 2 to the 8th is really 2 to the 4th times 2 to the 4th, right? Which is 16 times 16. But 16 mod 11 is 5. So that's congruent to 5 times 5 mod 11. Well, I'm not even say the mod 11 yet. I'm just trying to think about this. All mod 11. That equals 25, which mod 11 is probably 3. 3 more than 22. And so there you go. 2 to the 8th is actually 3 mod 11. And I did that without any sort of need to compute. So for some stuff like this, you can actually just compute much more simply than actually having to compute a big number and then reduce it. In fact, if you're sort of multiplying by 2 over and over again, it's almost like every time you get bigger than 11, you'd want to reduce it down. And each time. So that you never have to deal with any numbers larger than 10. Okay, so yeah, so that's just some helpful tips and just a reminder of some stuff I'm sure you already knew about. All right, I will stop.